Understanding Physics Hard Bits, and this video is an overview of particles. Now, it is possible, in fact it's possibly likely, that this is the first topic that you do if you do AQA Physics. So you're this youngster who's just finished their GCSEs, had a bit of a summer holiday, you go to your very first A Level Physics lessons, and you haven't got a clue. Now, in the specification, in the textbook, in the revision guide, this is the first topic. And I know for a fact that a lot of teachers teach this first, and that is bonkers. Okay, it's crazy. You should start with some forces and motion and electricity and waves, because they are the basics. Do they think, oh, we're going to make it interesting because this is a little interesting topic, you know, that'll get the students interested in it? You know, rubbish. It just confuses the students. It's just butterfly collecting. If you do it near the end of the course, then it makes so much more sense. Nevertheless, here it is. This is most of what you need to know. These are the kind of main points. So, let's talk about what you need to know for this particular topic. So, and it's basically, what is everything made out of? What elements make up everything? And there was a time when people thought it was just earth, air, fire, and water. And everything was a combination of these four things. We were a combination of them, and they had to be in balance. And if you had a little bit too much fire, then you had a fever. If you had not enough this, that, or the other. Okay, this was the basis of astrology. Astrology was a science that was taken very seriously. Galileo used to teach astrology to doctors, which I find that amazing. People took this seriously, but that was the model at the time. And in some ways it was useful as well. You could actually use it to make predictions and things, but it's not the model that we use now. We have these things called particle accelerators at places like CERN in Geneva. And basically what they do is they accelerate protons, so they're going ridiculously fast, and then the protons smash into each other. And what happens is that all the energy of the protons is changed into matter. And you create lots and lots of particles. You create a fruit salad of particles. You're not smashing the protons to bits to see what they're made of. What you're doing is you're changing energy, kinetic energy, into matter. And then we can see what different types of Lego brick are possible. Okay? And from detecting these particles, scientists now have a model of what the elementary particles are. And again, this model may change. There could be discoveries, and the whole model could be very, very different in 100 years' time. But this is the current model. This is what scientists currently believe everything is made out of. And it's called the Standard Model. The Standard Model of elementary particles. And everything is made out of this stuff here. Now, on the AQA Physics, you don't need to know all this. It's a bit selective. The ones that you need to know are those ones there. Okay? So, what do we need to know? We have fermions and we have bosons. Fermions are like proper particles which have mass. Bosons are airy-fairy messenger particles, as we will see. But these are the ones that you need to know, and you need to know some combinations of them as well. So the fermions, you've got quarks and you've got leptons. Quarks and leptons. Now, hadrons are made out of quarks. And you've got hadrons which are made out of 3 quarks, and they're called baryons. And hadrons are made out of 2 quarks, they're called mesons. I think mesons are middleweight. Hadrons are heavy hadrons. Baryons are 3 quarks, mesons are 2 quarks. Okay, Quarks can't exist on their own for reasons I'm not going to discuss here. But basically, hadrons are heavy, made of quarks. They feel the strong nuclear force. What's that then? You'll do it much, much later in the course. We'll talk a lot about that. So they're hadrons. Hadrons are made of quarks. The three quarks that we need to know: up, down, and strange. Leptons. Leptons are light. Hadrons are heavy. Leptons are light. Okay? For example, the electron. The electron is a type of lepton. But then you've also got muons, and you've got neutrinos. There's electron neutrinos and there's muon neutrinos. These are the ones you need to know. Okay, muons, if you do special relativity later on, there's an interesting experiment involving them. What do you need to know? Leptons are light. When an electron is created in beta decay, then you get an antineutrino must also be created. Muons decay into electrons. Do they? Yeah, how interesting. Muons decay into electrons. Bosons. Now, bosons are what we call exchange particles. They're not really particles like the ones on the left. They're more kind of, they carry forces. Now, imagine, look at these two people on skateboards here, and the person on the left chucks a ball, and because that person chucks a ball, they move backwards. And then when the person on the right catches the ball, they'll move to the right, won't they? And that's a kind of a model of what's going on. And the ball is the exchange particle. And we can think of that as carrying the force. Now, there are different forces. The electromagnetic force, which is like electric fields and magnetic fields, the force carrier is the photon. Not the kind of photon which comes out of your light bulb. They're called virtual photons. They appear out of nowhere and they disappear, and there's billions and billions and billions of them appearing and disappearing, and they carry forces. Bosons are force carriers. And this other boson you need to know is called the W boson, which is involved in beta decay. I'll talk a little bit more about that later. So we have our fermions. Fermions are firm. Fermions are firm. Bosons are airy-fairy. And then the fermions are either quarks or leptons. Now, I say particles. For every particle, there is a corresponding antiparticle. Well, I mean, for every type of particle, there is a type of antiparticle. Okay, so you've got your quarks, up, down, and strange, and you've got your anti-quarks, anti-up, anti-down, anti-strange. What's an antiparticle? Well, they're made from antimatter. And antimatter, what's antimatter? Well, it's the same as matter, only it's kind of like a bit like the opposite. If matter and antimatter got together, they annihilate each other. Okay, if you could make enough antimatter, you could make a bomb. Yes, because when it came into contact with matter, and all that mass would change into energy. Yeah, now antimatter does exist, but it doesn't last for very long for the reasons I've just said. There are some ideas that out there, there are galaxies made of antimatter. You know, and I don't know. At the beginning, just after the Big Bang, apparently, there was loads of matter and there was loads of antimatter, and there was this big war between matter and antimatter, and matter won. Yay! And so our universe is made of matter. Yes, very weird. But anyway, antiparticles, they've got the same mass as the particle, but they've got opposite charge. And as I said, they're made of antimatter. For example, a positron. Yes, a positron, which is, there's your positron there, is an anti-electron. And it's got the same mass as an electron, but it's positive. It's a positron. So you've got particles and you've got antiparticles. Two important interactions here, creation and annihilation. Annihilation, if anybody's played Unreal Tournament. Annihilation, I've already mentioned, when particles and antiparticles annihilate each other, then their mass is converted into energy. So an electron and a positron, if they collide, then and you get a couple of gamma photons, and you may know what a PET scan is, positron emission tomography, and if you detect the gamma photons, you can like build up an image of what's going on in the body. Annihilation, the opposite of that is creation. A gamma photon with enough energy can actually create a positron and an electron. Yeah, at CERN, I talked about CERN creating particles at CERN. They are created in pairs, and very often the pairs are, one of them's positive and one of them's negative. One of them is matter and one of them is antimatter. This is why we get the two spirals, because they're in a magnetic field. Oh, you haven't done magnetic fields yet. And so these charged particles spin in opposite directions. So creation and annihilation involve matter and antimatter annihilating or being created. So protons and neutrons, they've got 3 quarks, so they are baryons. Yeah, baryons have got 3 quarks. Remember, a proton is up, up, down. A neutron is up, down, down. They're made of up and down quarks, okay? These up and down quarks have a mass of a third of an atomic mass unit. An atomic mass unit is basically the mass of a proton. Yeah, think of it, that will do for the moment, yeah? The mass of a proton. So they're a mass of a third, there's 3 of them, so 3/3 is 1. An up quark is, well, up, it's positive, isn't it? Because it's up, it's happy, plus 2/3. A down quark, it's negative, minus 1/3. If you actually work out up, up, down, you'll see that the proton has a total charge of plus E, and that the neutron is neutral. That's why it's called a neutron. Also, you've got your anti-up. Your anti-ups have a mass of a third and a charge of minus 2/3. Your anti-downs have a mass of a third and a charge of plus 1/3. And you can get anti-protons and anti-neutrons as well. So protons and neutrons are baryons. They've got 3 quarks. In beta decay, now you should know that in beta decay, now in positron decay, beta plus, a proton changes into a neutron, doesn't it? Now what actually happens is that an up quark changes into a down quark. We say it flips into a down quark. In beta minus decay, a down quark flips into an up quark. Now, involved in this, it's a little bit more complicated. I said an up changes into a down. Well, it does. The up changes to a down, and for a very, very short period of time, it's something like 10 to the minus 24 of a second, you get this W plus boson. Yeah, we mentioned bosons as charge carriers. This is all to do with something called the weak nuclear force. So this boson is produced. The boson doesn't last for very long, and it decays into 2 leptons, the positron and the neutrino. Okay. A similar thing happens in beta minus decay. In beta minus decay, you get as I said, a down quark changes into an up quark. You get a W minus boson, which decays into an electron and an antineutrino. It's crazy, isn't it? It's butterfly collecting. And do you have to learn all this? Yes, you do. But anyway, there's your W boson there, which is decaying into the positron and the neutrino. Pions. Now, pions have got 2 quarks, so they are mesons. Do you remember, baryons have got 3 quarks, mesons have got 2 quarks, they're middleweights. And pions contain a quark and an antiquark. And you've got your pions, you've got pi plus, pi minus, and then there's two types of pi naught. Yes, and notice looking at them, you've got a quark and an antiquark, and the different combinations give you different types of pions. According to AQA, they are the force carriers for the strong nuclear force. Okay, according to everybody else, it's the gluon. Anyway, they're pions, and they're an example of a meson, a middleweight particle. Here are some more mesons. They're called kaons, and a kaon has got two quarks, so they are mesons, and kaons contain a strange quark. Okay, these are the different combinations here, your K minus, K plus, etc. Notice you've got a quark and an antiquark, and one of the quarks is this strange quark. Kaons can decay into pions. Oh, that's worth a flashcard, isn't it? Yeah. What are strange quarks? Well, strange quarks, a strange quark, S, has got a charge of minus a third. So an anti-strange would be plus a third. They are much heavier than your up and down quarks, about 40 times heavier. And strangeness, I'll talk a little bit more about it on another slide. It's a quantum number. And it has to be conserved. In any interaction, the total strangeness has to stay the same. Like the baryon number and the lepton number must be conserved in all interactions. So another type of meson is the kaon, and they contain a strange quark. Quantities that have to be conserved. From GCSE, you know conservation of energy, don't you? Well, here we say mass stroke energy because you've heard of E equals mc squared. Mass can change into energy, energy can change into mass, but the total, as when you do the nuclear physics later, will make more sense. The total stays the same. So mass stroke energy is conserved. Momentum is conserved. Oh, I remember that from GCSE. And then we have these other quantities which are conserved, which are integers. Yeah, charge is in integers of value E. Baryon number, the number of protons and neutrons has to stay the same. The baryon number has to stay the same. The lepton number, an electron has got a lepton number of +1. Yes, a positron has got a lepton number of -1. They have integer values, and then strangeness has to stay the same as well. Okay, we call these four at the bottom quantum numbers because they are either positive or negative integers which have to be conserved, have to stay the same. That's GASP. That's most of what you need to know. Okay, make an effort to learn it. Get some flashcards done. Try and get it into your head. Do you understand it? At this stage, I'd be very, very surprised if you did. By the end of the course, you will understand it better when you've done a little bit more physics. But for now, I'm afraid that's it. Okay, if you're doing AS, you must learn it full stop. Well, if you're doing A2 as well, you just need to learn it. Anyway, good luck with that.